Hi. 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 Is anyone in here?
Hello, everybody. Can you hear me?
Hey, Sid.
Hi. Good day. Hi, Juliet. Great to see you. How are you?
I'm good, but what I want to do is check my PowerPoint because we've had quite a lot of people having problems. So, Sid, since you're there, can you tell me if it works properly?
Go for it. Yeah. Are you going to drive yourself, Juliet?
I'd like to, so that's why I'd just like to check that this works.
Okay.
A lot of people haven't been able to get it into full screen.
I'm just letting Anish drive my PowerPoint, Juliet. I sent it to them yesterday, and it's in good hands.
They have mine in case, but let's just see.
Okay. I can see it in...
Not in full screen.
Not in full screen, correct. Yeah. Sometimes you have to double click on the first slide, Juliet. Yeah, I've had that issue.
There.
You don't just... Perfect. Loud and clear.
That's right. Okay,
You're great. Yeah. You're good to go. Thank you.
Stopped. Ah, perfect. Thanks, Sid.
Good.
How are you?
Perfect. I'm good. Good. Thanks, Julia. How are you?
What time is it there?
It's a little before 5 a.m.
Oh,
so
right now.
Not bright and early.
Have you got your pajama pants on and then just...
No, I'm fully dressed with shoes. So.
Wow.
But yeah.
Good morning, Sid. Good morning.
Satish, how are you?
Yeah, I'm fine. Sorry,
Great to see you. Good to see you. Where are you now?
Nice.
Hyderabad or?
I'm in Hyderabad at Inquire now. Yeah.
Good. Well, I'm really looking forward to this panel discussion.
Yeah.
I think the time is right for the Indian Ocean.
Yes.
Let's see.
Can I try sharing from my end the PPT?
Absolutely. That'd be great.
Anish, if this doesn't work, then you can share because I already sent the PPT to you.
Sure.
I would prefer to do that from my end.
It's fine. You can make it full screen, so I think it's visible.
You can see, right?
Yeah.
Yeah, let me make it full screen. Is it on full screen now?
That looks great.
It's on full screen, yeah.
That looks great, Satish. Yeah.
I will unshare now because others has to use this. Okay, thank you.
Looks good. Thank you, Satish.
Thank you.
Thank you.
I'm just trying something different there. Can you see my screen on full PowerPoint mode now?
Yes, Juliet.
Okay, I tried a different setting. That's much better. Cool.
Perfect. That looks really good.
Yeah, good afternoon, Shinoy, Anish, Sid. How are you?
Hi, Secretary
afternoon,
Rajiban. Good to see you, sir.
Yes,
Thank you for joining us today.
thank you, thank you.
Thank
So good
you.
morning. Is it too early morning there?
It's 5 a.m., bright and early.
Ah,
Good afternoon, Dr. Rajivan. Nice to meet
yeah,
you.
good afternoon, Shinoy.
Yes.
5 o'clock we get maximum peak sleep time.
Yeah, I went to bed a little early last night just to make sure.
Anish, can I try my presentation quickly if it is possible?
Yeah,
Yes,
yeah.
sir, please go ahead.
Okay. Is it
Yeah, it's
visible now?
Yeah,
Visible?
fine.
Okay.
Yes, you can. You want to try changing the slide, one or two?
Yeah. Okay.
You can put it on full screen slideshow mode and try that. Yeah.
Yeah.
Yeah,
Right.
it's changing, yes.
Perfect.
Okay. Thank you.
Thank you.
I will unshare now.
Who will say we should start at top of the hour? Who will lead that? Thank you.
Yeah, I'll be doing
Anish.
it. We'll just wait for 2 minutes.
Great.
To start.
Thank you. I just want to make sure someone is ready to start this. Thank you.
Yes, you can start the session. It's 2:30. It's live now.
You're driving my presentation, Anish. Yeah. Good afternoon. Good evening, everybody. Welcome to this plenary panel session on observations for services. I'm Dr. Sidney Thurston from NOAA's Global Ocean Monitoring Observing Program. and I'm also vice chair for the WMO Standing Committee on Earth System Observations. It's a real pleasure and honor for me to host this important discussion. This has been my North Star for 27 years since I've been with NOAA, the application of ocean observations for services. Could I have the title slide, please, Anish? Thank you very much. I believe very strongly that there's a lot of societal and economic benefits that can be derived from ocean observations, and that's what we'll be going over for the next 2 hours with our highly esteemed panelist. Next, please, Anish. This is our list. We're really honored to have Secretary Rajivan with us, talking about role of oceans on South Asian monsoon. Dr. Dilmahad, the Southeast Madagascar bloom, in observational and modeling perspective, Dr. Juliet Hermes, keeping the Agulhas current, and Dr. Satish Shenoy, ocean services in India and their impacts on the end users. These are the panelists. They'll have 20 minutes each to present their material. Next slide, please. And then we'll open it up. We'll go into a panel discussion for 30 minutes. And I've asked each of the presenters, the panelists, to address these 4 questions. What are the new developments towards sustainable ocean observing system? How can autonomous instrumentation, such as gliders and drones, be used to sustain ocean observations? How could the probable strategies to enhance multi-hazard early warning services, including predictions for the ocean, climate, and weather? And what will be our most important contribution to the UN decade? So I'd like each of the panelists to please think about that as we go into the 30-minute panel discussion. Next, please, Anish. I would like to set the stage. This is I put a link in the chat box. This is a paper we recently delivered to the World Meteorological Organization Bulletin. This is their most widely read paper or document in the WMO. And we were making the case for the use of ocean observations for Earth system predictions. Next, please. This is from the WMO. This is some of the impacts to economic sectors around the world, the economic value, if you will, of improving weather forecast for economic sectors such as agriculture, water supply, and transportation. But you can see improving weather forecast on many time scales has huge economic impact. Next, please. This is a new initiative. This is something I'm involved in for the WMO. This is the Global Basic Observing Network, GBON as we refer to it. And you can see that the left panel is the current state of observations. I don't need to get into all the details of the color coding, but the darker colors are not so positive, and the goal over the next several years is to turn to the right graph, the right picture, green dots. We want to really build a global observing system, and my job is to weave in the ocean observations into GBON, and you can see some of those on the bottom of this slide, such as sea surface temperature from drifting buoys. Next, please. This is what it's all about. This is taking the Earth system observations on the left, assimilating them into the models, into the predictions for forecast and products to deliver services to end users for early warning, can save lives and protects livelihoods. So for those users, you can think of agriculture, water resource management, health. You can name the economic sectors on the right. And there is a feedback loop here. We are constantly making sure we're taking the right observations to improve these forecasts. Next, please. It's a brand new world since I started 27 years ago at NOAA. We're looking at uncrewed systems now, sail drone, Argo, we're sending the data into the cloud. The supercomputer models are much more sophisticated, higher resolution, temporally and spatially. The data are flowing much more quickly to the models, and the forecasts are improving. But this is what our goal is to get these ocean obs data into the forecast to improve the models. Next, please. This is the Global Ocean Observing System. I don't know everybody's background on this panel, so I did want to mention this. To many, I know this is quite familiar, but this has been in existence for 3 decades, 30 years, Global Ocean Observing System. And I'd like to draw your attention to the left side of this schematic here. That is the Indian Ocean. We do have quite a few observations in the Indian Ocean. Next, please. These are the networks that were identified in the prior slide, and these are the 12 networks, and these are the WMO delivery of services. For example, drifting buoys can help with climate forecast, extreme weather events, and weather forecast. Next, please. So the point of all this is the Indian Ocean has a profound environmental influence on its own rim and oceanic environments, and on neighboring land masses far away from its own domain, including North America. So what stays, what happens in the Indian Ocean doesn't stay in the Indian Ocean. We have the Madden-Julian Oscillation, genesis in the Indian Ocean, but propagating eastward across the Pacific. And in fact, it impacts our week 2 forecast for North America. Next, please. This is the another new initiative from the WMO and the Intergovernmental Oceanographic Commission, IIOSC. This is a co-design concept whereby you start with an exemplar, some goal that you want to improve forecasting, and you work up the value chain. And this is where the WMO and the IIOSC will be working side by side, trying to improve forecasts. This is an example in the left panel of what NOAA's doing. We're trying to improve hurricane intensity forecasting through ocean observations. This is Hurricane Isaias on the left slide, and you can see on the right side our NOAA Hurricane Hunter with chutes where we go in and we measure upper ocean heat content, sea surface temperature, sea level pressure. Next, please. So I'd just like to wrap up by saying there are a lot of observations in the Indian Ocean. This is a very, very nice example of NOAA working with India's Ministry of Earth Sciences on the Omni Rama array and the Joint India National Center for Ocean Information Services, INCOIS, has stood up a very excellent data portal, joint data portal, so that the OBS are in place and the data are flowing. So let's listen to our panelists now. Next, please, to see how we can make all this happen. Thank you very much. And I'd like to start with Secretary Rajivan, please. Secretary Rajivan was the Secretary of Ministry of Earth Sciences of the Government of India, Advisor of Government in India, and the Director of the Indian Institute of Tropical Meteorology. Dr. Rajivan received his PhD in physics and has contributed immensely to the field of prediction of tropical monsoons using coupled models, extreme climate events, and teleconnections between reversing monsoons and associated physical processes. His main research interests are on Earth and atmospheric sciences, especially land, surface processes, and monsoon predictability. Secretary Rajivan has published more than 120 scientific articles and has received several awards and honors, including the START Young Scientist Award in 2001. So Secretary Rajivan, it's a real honor to be with you on this panel today. I'd like you to start, please. Thank you.
Thank you, Sid, for that nice introduction. My next 20 minutes or so, I'll be talking about role of the oceans on Indian monsoon variability. As we all of us know that India has 2 monsoons. One is southwest monsoon, June to September. Another is a northeast monsoon, October to December. Southwest monsoon has been studied extensively and very well whereas there's not much studies. There are not many studies on northeast monsoon. We don't know many things of northeast monsoon. Of course, monsoon, all of us know that monsoon varies in all time scale. It's starting from diurnal, synoptic scale, that means 4 to 5 days, the intra-seasonal, intra-annual, and also in multi-decadal time scale. We all know that monsoon, the basic dynamics of monsoon, ocean plays an important role. The land, ocean, temperature contrast as well as pressure contrast is the driving force for monsoon. And so ocean plays important role. So I'll be talking, of course, so this topic is not very new topic. We all know that oceans play an important role in monsoon. But what I'm going to say is the new insights which we got it from the recent studies the last 4 or 5 years or so. And what we know and what we understood now, and what are the gray areas where we need to really improve. And this is the monsoon variability figure. It shows starting from 1875 how all India monsoon rainfall varied. It says rainfall percentage departure, and all green are excess monsoon, and all reds are drought years we call, and blue years we call as normal monsoon. In overlying, I put a black line which shows the 31-year running mean, which clearly shows that there are multi-decadal variability. And you can see there are epochs in which monsoon has been very poor, and there are epochs where monsoon has been very good. And now we are in the low epoch, and there are the studies linking in this multi-decadal variability to global oceans. And this is a beautiful figure which shows the correlation between Indian monsoon rainfall and JJS mean OLR. OLR means outgoing long wave radiation, which is a proxy for basically convection. A low OLR means more convection, and less OLR is less convection. And less OLR is more convection, and more OLR is less convection. And so we have two big links coming out. One is over the Indian Ocean. You can see that's the south of equator, close to equator. You can see there's a link between Western Indian Ocean as well as Eastern Indian Ocean. It's a kind of a dipole. So typically resembles Indian Ocean dipole. And also then the famous El Nino relationship, ENSO relationship of the equatorial Pacific. And these are the two important relationships which we are getting in. And over the equator, there has been new studies saying that there are relationship between monsoon and also the equatorial winds. We call it equino, and oscillating between west and east, and depending upon the temperature anomalies over West Indian Ocean as well as East Indian Ocean, equatorial Indian Ocean. And this equino ASMR link has been now recently brought out, and positive anomaly in monsoon is basically associated with the low LR, higher convection over the western equatorial Indian Ocean. You can see the anomaly is the same. The color sign is same over the India as well as West equatorial Indian Ocean, whereas the East equatorial Indian Ocean anomaly is just opposite. So a more convection over the East equatorial Indian Ocean should really bring monsoon down. And similarly for over the Pacific. And ENSO ISMR link also we know very well positive ISR anomalies associated with the higher OLR, less convections. And extremes, and this is the equino which I was talking about. So if you really plot the phase diagram between equatorial wind over the equator during June to September, as well as the ENSO index over June to September, and you can see that this study by Godgill et al. In GRL, this the extremes of ISMR is well separated. And if you really see, look at only ENSO, the ISMR relationship, for example, many droughts have occurred without a El Nino. For example, years like 66, 74, 79, these are the drought years where there was no El Nino effect. So how we'll explain? So this phase diagram clearly shows that El Nino plus equin wind, equatorial winds can really explain all the extremes of both positive side as well as negative sides of the Indian monsoon. So the study clearly brings out the suggestion that both Pacific Ocean as well as equatorial Indian Ocean play an important role in the monsoon variability. I'm talking about internal variability. And of course, it's monsoon is equatorial Indian Ocean. Sorry, the equatorial Indian Ocean is also plays an important role not only in internal variability and multi-decadal variability. It starts from even extreme precipitation. Even in Tsunami scale, it plays an important role. This is a very famous paper by Roxy et al. 2017, which clearly shows that a few days before the extreme precipitation occurs, when it occurs over Central Indian Ocean, Central Indian region, there's a lot of moisture advection from Indian Ocean and moisture transport towards the Indian region, which brings. So Indian Ocean plays an important role, especially Arabian Sea and Bay of Bengal, play a very important role in making extreme precipitation events over the Indian region. And the time series very clearly shows that events the frequency is increasing. And right hand side, even the Indian Ocean plays an important role in the interglacial monsoon. So this is a very recent paper which appeared in PNAS in 2020, just a few days back. It clearly shows the sustained warmer surface temperature in the equatorial Indian Ocean played an important role in interglacial increased convective rainfall, but dampened ISM and in summer monsoon intensity. So the paper clearly says that tropical Indian Ocean played an important role of lesser monsoon rainfall during interglacial monsoons, interglacial period. And in addition to both the Pacific as well as Indian Ocean, there are also some studies suggesting the link between Atlantic zonal mode, Atlantic Ocean and Indian monsoon. A very long time back, we have studied in 2008 paper in which we linked the relationship between SSTs or Atlantic, and this parameter has been used by IMD for seasonal forecast in the empirical model. And recent studies of Atlantic zonal mode has been brought out. But of course, we need to really understand more about the role of in the Atlantic Ocean on internal variability. And interdecadal variability, this paper very clearly says that both Pacific as well as Atlantic as well as Indian Ocean play an important role on monsoon interdecadal variability. But I will be talking mostly now on the Indian Ocean anomalies and how they are related to Indian monsoon. This is a very famous diagram of secular variation of relationship between Indian monsoon and El Nino. We know that Indian monsoon and El Nino are very related and negative correlations exist. More for some El Nino even we normally tend to get less rainfall. And this is a very famous paper by Krishna Kumar which appeared in Science in 1999, which clearly shows there's a lot of multi-decadal kind of variation between the relationship between El Nino and Indian monsoon. And when somewhere in the 90s, late 90s and all, it went bad. It weakened. The relationship is weakened. You can see that there's a horizontal line. That's a significant line, line of significance, statistical significance, and it has gone less than that. So that is the period. That's the time when Krishna Kumar wrote that paper saying that it is monsoon relationship is weakening. Relationship is weakening, but it has picked up again. Now, recent few years, if you see, monsoon has really, the El-Nino relationship has really strengthened further. And now still ENSO plays an important role in monsoon variability. The question is why? Why this kind of changes has occurred? And who plays an important role in this kind of further strengthening of this relationship? And this is the paper, again, last year it has come out in Geophysical Research Letters, studying Indian monsoon rainfall ENSO relation from its recovery in the 21st century. And they say that clearly Indian Ocean assist anomaly is playing an important role. I'll come to that small brief discussion about that. This is the three plots which shows the correlation between monsoon rainfall and SST and winds at 850 millibar between different periods, 61 to 80, 81 to 2000, and 2001 to 2020, which clearly shows that there are significant variation of the relationship. We can see that 81 to 2000, the relationship was very weak over Pacific as well as Indian Ocean. And also there is a significant variation over Atlantic. You can see just north of South America, you can see that there is a relationship is also changing between the three epochs, 3 decades. And so this, what the people have done is just they try to analyze the AMI brands, AMI atmospheric model in an inter-comparison project, where the model is atmospheric model, but they run it using observed SST. And they try to see that whether this kind of strengthening of relationship has been brought out by these models. And very, very interestingly, this model, the study clearly shows that the thick line in the figure C clearly shows that it has the AMI model clearly shows a kind of a weakening than strengthening of a relationship between Indian monsoon and the ENSO. So which clearly says that SSTs play an important role because these models are run by observed SSTs. So SSTs play an important role. And so the top and right one very clearly shows that the largest negative correlation between the so-called the index which they use is correlation is seen over the Indian Ocean. You can see the blue, a lot of blue colors are there over the Indian Ocean, the top figure, and which clearly says that this kind of strengthening of the relationship has come from the Indian Ocean. And I will straight away go to see what they have done is this relationship between El Nino and the Indian monsoon. They have bifurcated into two epochs, where the tropical Indian Ocean was warm, while the tropical Indian Ocean was cool. And if you really see the two plots in item number C, you can see that correlation is minus 0.89 when this El Nino, so the relationship is very stronger when the tropical Indian Ocean was warmer. And whereas the tropical Indian Ocean was cooler, the correlation is only 0.006. So Indian Ocean plays very important role, and of course this relationship is explained by, for example, circulation anomalies, 200 millibar divergence veins. So we can theoretically explain why this kind of relationship is strengthened due to Indian Ocean and what Indian Ocean is really playing a role. And the question is, the next question is whether the Indian Ocean, Indian monsoon relationship is well produced in climate model. That's the question which we ask, and this is a good figure which clearly shows the top one clearly shows the SST and SST ISM Indian monsoon correlations of using observations, and bottom one is a model, climate model, which India IMD is using for their seasonal forecast. It's called Monsoon Mission Climate Forecasting System. It's basically your NSUB model, and which clearly shows the relationship over the Pacific is very much stronger compared to observations, whereas the Indian Ocean, you see that the relationship is not really reproduced. So the models, the message is the models don't produce the relationship between Indian Ocean and monsoon rainfall very well in the climate model. And this another paper, the left-hand side, you can clearly shows that the top one is the observations and the bottom one is the model, which will clearly show the Indian Ocean is not well reproduced in the model. For example, the Indian Ocean anomalies and the Indian anomaly, Indian monsoon rainfall anomaly and the West Equatorial Indian Ocean should go phase in phase, but in the model this is just opposite. And this is seen in take any climate model, this observation, this anomaly is seen. So the models in general don't reproduce the good relationship between Indian Ocean and Indian monsoon. This is another example on the climatology. They have seen so many models, and all the models show the same problem. So it's a systematic issue in the climate model. And another paper. This is a very interesting paper. It also shows that we know very well these models. We also reproduce a dry monsoon rainfall over the central Indian Ocean. And this paper very clearly shows that it is there in all kind of climate models, CMIP 3, 5, and 6. It's systematically the dry phase of the dry bias of the monsoon rainfall is seen in the model. The question is why? And they come out with the theory saying that this the bottom on the left-hand side very clearly shows this is observations minus the model. Observation minus the model, which very clearly shows the Indian Ocean, the model reproduce more SSTs. The climate model tend to produce more higher SSTs than compared to observation over the Equatorial Indian Ocean. So that may be playing an impact. So it's very systematic. Warm bias is there in all the climate models over the Equatorial Indian Ocean, which may be playing an important role of the dry bias over the central Indian region. And first of all, it produces more convection, then less reduce the rainfall over Indian monsoon rainfall region, and also it affects the northward propagation of so-called ITCZ, ISO pattern, etc. So the Indian Ocean warm anomaly bias is very systematically seen in all the models. And it is seen in northeast monsoon. Northeast monsoon in the October, November, December. And there also the relationship between ENSO and monsoon rainfall, northeast monsoon rainfall, also has a secular variation. It has some epochs it is stronger, which is very clearly seen in this figure. You can see that there are epochs in which is stronger correlation, in other epochs is weaker correlation. And in general, the northeast monsoon rainfall and El Nino are positively correlated, whereas the southwest monsoon rainfall and El Nino are negatively correlated. When we come into the northeast monsoon, the relationship just gets changed in sign. And these models don't reproduce that change in sign. the model still produce the negative correlation. So that is a big issue of this we try to explain in this is one of my students' PhD thesis a long time back. He tried to reproduce this kind of relationship using observation, try to explain why that kind of relationship, the secular variation is normally seen. And we find that it is basically driven by the Indian Ocean atmospheric winds over the lower troposphere. And 2 years, the recent 2 years, 2010 and 2021, last year, it was a La Nina year. It was typical La Nina year, 2010 as well as 2021. But monsoon, northeast monsoon was highly excessive. And last year, Tamil Nadu, especially the states like Tamil Nadu, got numerous floods, at least some 5-6 flood events that they experienced, and they have excess monsoon in this. So the question is, why in a La Nina year we should get excess monsoon, northeast monsoon over the South Peninsula? That's the question we ask. And there are only some 3-4 examples are there where we have La Nina, but we had excess monsoon. And this is the monsoon. If you really see that it's a typical La Nina phase, but what we are seeing is North Indian Ocean, the Bay of Bengal as well as Arabian Sea was much warmer both the years, both 2010 as well as 2021. The question is whether Bay of Bengal played an important role in making the northeast monsoon more active during these 2 years. This is a basic question which people ask. And this is also 2021 monsoon. You can see that it's typical La Nina year, and but we had excess monsoon. But you can see the Bay of Bengal was much warmer. And these observations, this kind of relationship, whether models are reproducing, no, answer is no. And which very clearly shows the observed rainfall and multimodal rainfall, the correlation is much poor. And if you really plot the rainfall and the SST, you get the observation, you get a correlation of 0.32 or so. But in the models, we produce the correlation of minus 0.31, just opposite. So the models don't really reproduce, don't learn the lesson that Southwest monsoon is no more. Now we have different basic ground, basic flow, and we have a Northeast monsoon, but the relationship is changed, but the models don't pick it up. And this is seen in many papers, and many studies saying this is the climate models again. And so the basically, if you really see all the anomalies of all the model results and try to understand why these models don't reproduce the correct relationship between Northeast monsoon, Indian monsoon, Northeast monsoon and El Nino, the answer really leads to the important role played by Indian Ocean. So Indian Ocean may be making a kind of a relationship, kind of a physical mechanism, maybe reproducing some kind of physical mechanism in which monsoon and northeast monsoon becomes active during for some La Nina phase, and El Nino years you get suppressed rainfall, etc. So all these studies very clearly demonstrate Indian Ocean plays an important role. So this is a summary of what my presentation is. So we need more and more of systematic observation over the Indian Ocean. I saw the beautiful figure of shown by Sid, the Global Ocean Observation Network, huge network. But probably we may have the feeling that it is required, more and more observations are required, and also focused modeling efforts. Ocean models need to improve, especially over the Indian Ocean. Indian Ocean, they have systematic biases in the SSTs, systematic bias in the rainfall relationships, and we may be making mistakes in the initializing the climate model using Indian Ocean observation. So more observation from the Indian Ocean, whether that may improve the model initialization. These are the questions which we need to ask, and more observational campaigns we need to do. So I would like to, Sid knows about this program which Ministry of Earth Science is going to launch with the help from US partners, and Sid is also an important partner. It's called Enhancing Knowledge of the Arabian Sea Marine Environment through Science and Advanced Training. So this is going to be launched very soon. So this kind of observational campaigns will definitely give us more clues about the role played by Indian Ocean on monsoon variability. With this, I will stop here. Thank you very much for giving me this opportunity to talk to you. Thank you very much. Thank you, Sid.
Thank you. Thank you very much, Dr. Rajivan. That was just an excellent update. I like seeing all those updated results. Thank you for bringing us up to date on monsoon research. We do have time. I would like to take 1 or 2 quick questions if we have them. I'm looking in the chat. I don't see any questions there. Secretary Rajivan, I would like to ask what new observations would really deliver some results, would raise the bar on understanding and forecasting monsoon? Where would the observations be best spent?
Or the Indian Ocean, you mean to say?
Yes, Indian Ocean. Yeah.
Indian Ocean, the actual mixed layer data is more important for initializing the models. So that's what my feeling.
Excellent. Thank you. And I do see Satish Shenoy raised.
Shenoy is raising hand.
Yes, absolutely. Please,
Yeah,
Satish.
Thank you, Dr. Rajiv. It was a very nice, quick but very elaborate presentation. I will just have a question on the. You showed that beautiful curve, which showed the strengthening and weakening of monsoon and with respect to El Nino. That was for the southwest monsoon. Is there a similar picture for northeast monsoon? What is the story?
Northeast monsoon also has the same kind of relationship. It's some phases it is positive, some phases it is negative. So it's the same kind of relationship. Only thing is the relationship is just opposite, but it also has a large secular multi-decadal variability. In some decades the relationship is much more stronger, some decades is much weaker.
Thank you.
So fundamentally something is happening.
Great.
Thank you very much.
Thank you. Thank you.
Thank you very much, Dr. Rajivan. We would like to move on now, please, to Dr. Femi Dilmahamad. Please, Dr. Dilmahamad is Ocean Frontier Institute postdoctoral fellow at Dalhousie University, Halifax, Canada, in collaboration with Geomar Helmholtz Center for Ocean Research in Kiel, Germany. Dr. Dilmahamad completed his PhD in physical oceanography jointly from the University of Cape Town, South Africa, and University of Brittany, Brest, France, on the topic, the biophysical processes controlling the southeast Madagascar bloom. His research is primarily focused on role of mesoscale eddies for the Labrador Sea's carbon uptake. He is an active member of Early Career Scientist Network of IIOE2 and postdoc representative of Early Career Ocean Frontier Institute researchers. Dr. Dilmahamad, the floor is yours, please. Thank you. We can't, you're maybe mute, Dr. Dilmahamad.
Is that better now?
Much better. Please proceed.
Great. Thank you very much for giving me the opportunity to talk today about my PhD work. And so let's move a bit more towards a regional biophysical feature of the Indian Ocean, which is the Southeast Madagascar bloom. So I would like to first of all start with this figure here, which shows the satellite altimetry of mean chlorophyll A from February 2006. And as the title mentioned, the Southeast Madagascar bloom here is very well shown in this figure. So this figure really gives an exceptional view of how big and massive this Southeast Madagascar bloom can be. Like, for example, it can have a length of approximately 2,000 kilometers and a width of 1,000 kilometers, which is pretty massive for this region of the ocean. And it is also like one of the most compelling features of the South Indian Ocean in terms of ocean color time series. And hence, when it occurs, this bloom is very important because it can play a fundamental role in the biochemical cycling of elements, regulation of atmospheric carbon dioxide, and of course, the oceanic life. And it is also very important for all the surrounding areas, all the surrounding islands here, such as Madagascar, Réunion, or even Mauritius, because it can really impact the fisheries into this region. So next, what we can also see from this figure here is how filamentous this structure of this bloom is. So it really can point out to the possible role of eddies in creating this bloom. And it also occurs into quite an oligotrophic region. So moving on, I want to show here a time series of chlorophyll A concentration into the bloom box here. So what we can observe is that if we focus into austral summer, we can observe that the bloom occurs in if we focus into austral summer, we can observe that the bloom occurs during austral summer, always occurs into austral summer, but not every year. For example, in 1999, 2000, we have a bloom, but in 2001, absolutely nothing. So this bloom really has a really erratic interannual variability. I want to show next this figure because these shows the three major blooms, February 1999, February 2006, and February 2008. And it again gives a really exceptional view of the spatial structure of this bloom here. But most importantly, how variable this bloom is in terms of its spatial structure. Here, I'm comparing April 2002, April 2003, and April 2004. And we can see how different this bloom looks like from one year to the next. Most impressively, when we compare January 2007 and January 2008, we can see nothing. There's not much happening in 2007, but this massive bloom in 2008. So there has been only one cruise in 2005, which went through this bloom. And what they found is that south of Madagascar, the bloom was composed of trichodesmium, and southeast, it was mostly composed of Rhizochelenia diatoms. Both of these species being nitrogen fixers. But this also shows us the lack of observation that we have, the lack of in situ observations that we have into this region. Moving on, I want to just give you a brief view of how the local circulation looks into this region. So first of all, we have the southeast Madagascar current, which flows along the coast of Madagascar towards the pole, and then it rounds the southern tip of Madagascar and joins the Agulhas current either as a main flow or as mesoscale eddies. But this current also drives a local upwelling south of Madagascar here, which could be very important. What we also have into this region is an opposite current flowing towards Australia, which is called the South Indian Ocean countercurrent. Also, we have westward propagating surface and subsurface intensified eddies traveling from Australia towards Madagascar. So this shows how this region is very complex in terms of its dynamical features. So moving on, we want to understand what is causing this bloom. So we have to look at observational data that we have. Apart from satellite data, auger flows are very important in trying to understand different features of the ocean. Here, what I'm showing is the number of auger flows that we have in the ocean at the moment. And we can see that we have a few into the Indian Ocean, obviously. But if we move on from normal auger flows to biogeochemical auger flows, we can see that in the South Indian Ocean, there's not much biogeochemical auger flows which are present. So this is something that I think we need to look to work towards so that we can have a good view of the physical but also the biophysical features happening in the Indian Ocean. So what we did in our study is that we tried to look at how the water column structure looks like within a bloom region and outside of a bloom region. So we collocate these auger profiles, which give us temperature salinity data, into our bloom region. Of course, as we can see from this figure, there is a meridional gradient of sea surface salinity. So to prevent any bias, we decided to separate these regions into two, into a fresher side and a saltier side. And when we look at the water column structure, here what I'm showing is the temperature. In red, it's within the bloom region, and in black, within outside of the bloom region. And this is temperature and salinity. So the main findings from this is that the bloom occurs within a shallow stratified mixed layer. But most importantly is that when the bloom occurs, the salinity in the upper layers of the water column seems to be lower. So this begs the question, where is this low salinity water coming from? So when we have a look at the curve, which shows us the climatology of sea surface salinity, we can observe that the southeast Madagascar current actually has a low salinity signature. So this is one piece of the puzzle here. Moving on, we also tried to link this bloom to other processes. So one of the previous studies indicate the possible importance of this upwelling region south of Madagascar in creating the bloom. So what we expect is that whenever there is an increased upwelling intensity, there will be a bloom. However, what we found is that is the exact opposite. Whenever there is a major bloom into the southeast Madagascar region, the local upwelling south of Madagascar is reduced. So that goes against what we originally thought. So we also tried to link this bloom to climate processes such as the Nino 3.4 index. So what we found in this case is that the bloom seems to occur during the mature phase of La Nina. So this is very important. So the main findings from an observational point of view is that the bloom occurs within a shallow stratified mixed layer. Whenever there is a bloom, the upper layers of the water column is lower in salinity. The blooms coincide with the mature phase of La Nina years, and also we have a decrease in the current-driven upwelling south of Madagascar during the bloom. So this leads us to propose a new hypothesis. As you can see here, is that during La Nina years, what we expect is that we have a stronger south equatorial current. And this stronger south equatorial current will translate into a stronger southeast Madagascar current. This stronger southeast Madagascar current now will be more unstable and could potentially detach or early eutrophics from the coast towards the open ocean here. And by doing so, it will advect nutrients, phytoplankton biomass, or even trace elements from the coast towards the bloom region. And at the same time, this current-driven upwelling south of Madagascar will be reduced. So that hypothesis goes in line with our findings. And if we have a look now at a composite of sea level anomaly from altimetry data during bloom and non-bloom events, we can observe that during the bloom, there is a possible pathway from the coast towards this southeast Madagascar bloom region, which goes again in line with our hypothesis. During a non-bloom one, this pathway doesn't seem to be here. So these are all findings from an observational point of view. Of course, we want to understand more about this bloom. So what we did is that we now try to look at this bloom from a modeling perspective. So we set up a regional configuration model based on CROCO, the physical component of this model, and we coupled it with PISCE, which is the biogeochemical component. So this is our parent domain of our configuration, which is at 27 kilometer resolution. And inside we have an embedded nest, which is at 9 kilometer resolution. But I want to point out one thing here is that from the only crews that went through that bloom, they showed that nitrogen fixers could be an important layer into the generation of this bloom. However, our model here does not parameterize for these nitrogen fixers, but we also hypothesize that possibly other biophysical processes might contribute to the generation of this bloom. Moving on, first of all, when we work into a modeling from a modeling perspective, we need to see if the model is actually reproducing the bloom. So if we have a look here at two periods in the surface layers into this region, there doesn't seem to be much happening in the surface layers. However, if we look into the subsurface layers, we can see more enhanced chlorophyll A concentration, which could potentially link to a bloom. Next, what we did is that we look at the time series, similar as we did for satellite altimetry. And what we observe is that there seems to be a bloom happening in austral summer into the model, and it also seems to be happening quite erratically, as can be observed from satellite. So this gives us a bit of confidence towards the model, and hence we can use the model to understand this bloom. So similar to what we did in observations, we tried to again look at the vertical structure within the bloom and outside of the bloom. Again, we have the same findings. The bloom occurs within a shallow stratified layer, and the upper layers of the water column structure seems to be less saline. So, like I mentioned, similar vertical structure associated with the bloom, both in observations and in the model. And now, again, if we look at sea level anomaly composites during bloom and non-bloom, we can observe that during bloom, it seems to be more energetic, more energetic processes happening southeast of Madagascar, which could potentially create this pathway from the coast towards the bloom region. Another interesting thing that we can do with the model is to quantify nutrient fluxes. So what we did here is that we tried to look at how much nutrients are actually coming from the coast towards our bloom region, which would be in line with our new proposed hypothesis, or how much nutrient is actually being advected from the deeper layers, which would be the equivalent of local upwelling. So what I'm showing now is two specific bloom events into the model, and the top row shows chlorophyll A concentration. The middle row shows the nutrient fluxes. In blue, we have the nutrient fluxes from the coast. In red, the nutrient fluxes from the subsurface, and the lower row shows salinity into the region. And in 2005, what we can see is that the bloom is mainly driven by nutrients coming from the coast, which again goes in line with our hypothesis. And at the same time, we have an intrusion of low salinity waters when the bloom occurs. In 2010, what we found is that the nutrient fluxes from the coast initiate the bloom, which is then sustained by nutrient fluxes from the subsurface, again in line with our hypothesis. So from a model perspective, what we found is that 6 out of our 8 simulated blooms occurred during a time period of enhanced nitrate fluxes from the coast. So like I mentioned before, this is an additional piece to this really intriguing Southeast Madagascar bloom. So from an observation, what we propose a new hypothesis that an early detachment of the less stable Southeast Madagascar current during La Nina years will advect nutrients, trace elements, or phytoplankton from the coast into the bloom region. And we use the model to test this hypothesis, and the model actually corroborates this hypothesis, suggesting that the fertilization of the simulated Southeast Madagascar bloom occurs concurrently with an early detachment or a retroflexion of the Southeast Madagascar current. So from there, we also did another study to look at this early detachment or early retroflexion of the East Madagascar current. And this study actually shows for the first time that the East Madagascar current has 3 phases: an early retroflexion, which is what we suggested, a canonical retroflexion, which is when the retroflexion occurs more south of Madagascar, and when there is no retroflexion and there is a connection between the East Madagascar current and the Agulhas current. And also this study showed that whenever we have an early retroflexion, the local upwelling intensity into the region, as you see here, is decreased, which is again in line with all our findings. And now if we take, for example, all the events of early retroflexion that we have been observed, and if we do a composite of the chlorophyll A concentration during that period, we can find that there is a presence of the Southeast Madagascar bloom during these events of early retroflexion, which again shows that the early retroflexion is a contributor to this austral summer bloom. And I want to end this talk by showing this last slide here, which is here I'm showing chlorophyll A concentration in December 2019 and January 2020, which from the current time series of ocean color is the strongest Southeast Madagascar bloom ever recorded, as we can see here, massive bloom. And there have been a new study which came out last week, which shows that, of course, what we expected is that whenever there is a bloom, we expect this region to be an ocean carbon sink, hence attracting carbon dioxide from the atmosphere towards the deeper ocean, and that during a non-bloom event, we expect this ocean to be either a carbon source or an equilibrium. And this new study actually showed that in December 2019, this bloom here actually contributes to an ocean, to a carbon uptake of approximately 0.8 teragram of carbon during December 2019, and approximately 1 teragram of carbon in January 2020, which is quite big for this region. And this also shows the importance of this new study, because this new study uses a new carbonate system observations, which is part of the WASO project, which is the Océan Indien Service Observation, which I think would be very important to have all these new observational systems in place into the Indian Ocean for a better understanding of the physical and also the biogeochemical features happening into the Indian Ocean. And from there, I would like to thank you all for your attention, and I'm happy to take any questions. Thank you very much.
Thank you so much, Dr. Dilmahamad, for that really clear and forward-looking presentation. It's very, very encouraging to see the progress being made. I see Satish Shenoy's hand is up. Please, Satish.
Yeah, thank you, Ahmad, for the nice presentation. Because we don't know much about those regions, so this was a very good information for me. My quick question is, you said that your new hypothesis says that the timing of detachment of southeast Madagascar current, that is what is causing the bloom, because it advex those nutrients from the coast into that region. So if the timing is late, for example, the current get detached a little later or much later, will it not create that bloom then?
Yes, thank you very much for this question. And so I want to point out here from this new study, what we show is that of course the early retroflexion of the East Madagascar current, which would advect these coastal waters rich in, of course, low in salinity, first of all, and also rich in nutrients, trace elements, or phytoplankton into the bloom region. So this early retroflexion can actually occur any time of the year. But what we did here is that we took only the events which are happening in austral summer, because as I mentioned first, this bloom occurs in austral summer. And what I expect is that whenever it's happening deeper later in the year, not in austral summer, we will have a bloom, but it's not this kind of bloom, because of course this region, if I go back to my time series, we can observe that usually there is a winter bloom. Most of the years there is a winter bloom. It's only the austral summer bloom which is very erratic, and this also has one contributor would be the mixed layer depth, because we expect the mixed layer depth to be shallower and the water column to be more stratified into summer compared to winter. So I'm expecting whenever the early retroflexion occurs in winter, we will have a bloom, irrespective of there being an early retroflexion or not, just because the mixed layer is deeper, there's more mixing, there's more nutrients towards the surface. But whenever this East Madagascar current retroflexion occurs in austral summer, that's when we have this austral summer bloom. But again, this is one, like I mentioned in one of my slides, this is one piece of the puzzle. This whole system is not fully understood, and one way to do that obviously would be to get all these really nice autonomous vehicles like gliders into the ocean, into this region, and to really get a really detailed view of what's happening into this region during a bloom.
Excellent. Thank you very much, Dr. Dilmahamad.
But it will be much weaker. That's what it is.
Thank you.
Thank you.
Okay, excellent. Thank you very much, Dr. Dilmahamad. I would like to move on now to Dr. Juliette Hermes. And I have the honor of introducing Juliette, is the manager of the South African Environmental Observing Network, SEON, Iga Gassini node for marine offshore systems. She has been invited by the World Meteorological Organization to serve on the steering committee of the Global Climate Observing System, GCOS. Her research interests are in the field of Earth's climate system, climate change, impacts of climate variability, climate modeling, and their application to national economic development. Dr. Hermes regularly interacts with the other SAON nodes focused on observation and monitoring to gain a better understanding of variability and change within the different biomes, including coastal and various terrestrial nodes. She is also actively involved in education outreach and support through SAON, and being a research associate at the University of Cape Town, Juliet co-supervises students and gives lectures. Thank you very much, Juliet, for being with us today, and please, the floor is yours. I think you may be muted, Juliet.
Thanks. There we go again. Thanks, Sid. Hope you can see my full screen now.
Looks great.
Great. There we go. So thanks for inviting me to give this presentation. And I'm very proud at the moment to be following one of my PhD students after they've given such an excellent plenary presentation. So well done, Femi. That was really, really good. And thanks to the organisers for really making this virtual meeting seem as real as possible. But I have to say, I really wish I was in Goa with you all now, and hopefully next year. So just to acknowledge my co-author Tammy Morris on this presentation, but also all of the colleagues that I work with who are involved in research for the Southwest Indian Ocean. So we all know that the Indian Ocean is warming faster than any of the global oceans, and that food and water and energy security in the Indian Ocean rim countries and islands are so intrinsically tied to its climate, with marine environmental goods and services, as well as trade within the basin underpinning their economies. So there's a range of societal needs for Indian Ocean observations arising from the influence of the regional phenomena that we've heard so much about during this conference and climate change on, for instance, marine ecosystems, monsoon rains and sea level. But is this information really reaching society and policymakers? How much of the excellent work presented during this week is reaching the public? And how are we really keeping ocean sciences and observations current? So we've heard about the INDUCE, Indian Ocean Observing System from ROXY. It's a sustained observing system that monitors basin scale ocean atmosphere conditions, whilst also providing flexibility in terms of emerging technologies, scientific and social needs, and a framework for more regional and coastal monitoring. And the utility of INDUCE is ultimately dependent on the identification of and the engagement with end users and decision makers. So on making the sort of practical accessibility and transparency of data for the range of products and decision-making processes. So this sort of knowledge of the status of the Indian Ocean climate and ecosystems and predictability of its future really depends on a wide range of socioeconomic and environmental data, a significant part of which is provided by INDUCE. Now we know that more recent studies suggest that Indian Ocean has stored a sort of astounding 30% of the global oceanic heat uptake from the atmosphere over the last 2 decades. And this heat uptake has strongly contributed to the temporary slowdown in the global surface atmosphere temperature warming. Now the heat is thought to have largely entered the basin from the Pacific via the Indonesian through flow. Yet the relationship to the warming in the southern subtropics and to regional sea level rise is unclear. And so its ultimate fate regarding a possible return to the atmosphere to contribute to a future acceleration in global warming is unknown. And this motivates the need for observations that can monitor the dominant oceanic heat fluxes of mass and heat and ultimately constrain these basin scale budgets associated with the decadal variability and change. So INDUCE recommended the establishment of boundary flux arrays in both the Agulhas and the Luan currents, and an enhancement of Indonesian through flow monitoring and an increase in observations of the deep ocean. So boundary currents dominate the poleward transport of warm water and the equatorward transport of cold water, and they're the major drivers of climate variability and extreme weather events, and as we've heard and will hear on Friday, marine heat waves. So communication between the coast and open ocean is also regulated by the boundary currents that flow along these continental slopes. And this affects ecosystems, sea levels, flood levels. So the focus of my talk is really on the importance of the Western Indian Ocean and how measuring the Agulhas current is, which has been identified as a Tier 2 priority in the induced decadal review, plays such a dominant role in basin-wide heat and freshwater fluxes. In fact, sustained observations of the Agulhas system, which is the current and the Mozambique Channel and the East Madagascar current, has been likened to having a finger on the pulse of climate variability over the Indian basin, because the Agulhas is such a natural integrator of water mass and dynamical signals throughout the basin. So I've just put these figures up because I wanted to highlight that for Western Indian Ocean countries, particularly South Africa, Mozambique, Tanzania, and Madagascar, measurements of the Greater Agulhas current system and its leakage are a real priority given its influence on the regional climate and ecosystems. So you can see here some of the main weather systems that are influenced by the Agulhas current, and also this image just shows chlorophyll to give an idea of the current-driven upwelling off the east coast of South Africa. But there's no integrated observing system for this region. So current strategies used to monitor boundary currents vary, and they're composed of individual and partially coordinated efforts. So at global scales, you've got the Argo array collecting ocean physics and biogeochemical parameters and really providing comprehensive coverage offshore of the continental shelf. There are satellite measurements of sea surface height, temperature, salinity, and ocean color, which clearly identify the signals of mesoscale features at the ocean surface. You've got surface drifters, which take measurements of the currents, but there's a real need for finer spatial and temporal resolution close to the shore, and this can be addressed with more regionally focused efforts. So ocean gliders can provide sustained or targeted observations across boundary current systems. And the Ocean Sites network of moorings has some of the longest in situ time series at strategic locations within boundary currents. And also you've got the XBT network, which provides repeat temperature sections with a fine spatial resolution across boundary currents. And each network in the Global Ocean Observing System provides observations that complement each other in their efforts to monitor boundary currents. And we really sort of need this further expansion of the suite of observing platforms. And this, may be enhanced by technologies such as autonomous surface vehicles. And I think we'll discuss that in the panel discussion afterwards. But what we have to consider is that several boundary currents they reside within countries' EEZs. So observing boundary currents kind of depend on the regional efforts and cooperation. So regional pilot studies have been suggested as a mechanism for investigating this cross-platform use of ocean observing systems to monitor particularly those boundary currents that are understudied. Now, crucial to this effort is interacting with regional stakeholders to understand their needs and challenges. And it's really in this way that we can develop a fit-for-purpose, multi-instrument, multi-variable monitoring system. So focusing back on the Agulhas current. Since 2010, there was the Agulhas Current Time Series, which was led by the US, and this was then followed by the co-led South African and US Agulhas System Climate Array, which is shown here and here. But there were issues with ships availability and lack of resources, which resulted in the early termination of ASCA in 2018, which possibly with COVID ultimately wasn't such a bad thing. But these other mooring arrays off South Africa are still being sustained. So if we look a little bit about what we know about the Agulhas current, the seasonal variability properties are really not well understood because there's been such few data collected during austral winter. So the work done by Beale et al. With the mooring array and Hutchinson et al. Who used models showed that there is this seasonal cycle, but that it's not yet correctly captured in models. And a recent study by Braby uses a decade worth of observations over the same transect line of the Agulhas current and includes the first 2 full-depth winter surveys of the Agulhas current. Now, if you go to sea in winter in the Agulhas current, it is quite a thing to do CTDs down to the full depth. So having 2 full-depth winter surveys is quite a thing. So they investigated changes in the water mass properties from one season to another and showed that in summer, when the Agulhas current is stronger, there's nutrient-rich water masses located offshore, and at depth, these are observed to migrate upwards onto the continental shelf. And this really isn't apparent during winter. So just to highlight really how we managed to do these winter transects, they were made possible thanks to a program called Semester, which is South Africa's floating university, and the brainchild and passion of Professor Isabel Anzorb. So through Semester, repeat research crews over the IIOSC line with carrying out of various different observations has occurred, but at the same time, it's been training and inspiring postgraduates from all over South Africa. So it's really through combining both the new technologies and the international partnerships, along with the traditional methods and science engagement, that we're able to keep the Agulhas current. And we hope to roll out the observing system, the ASCA array, over the next 3 to 5 years. The South African government has really embraced the need for this observing system, and so this will be sustainable based on South African investment, but also with support from the international community, which is really key. So it's really key that these regional efforts are supported because they're generally considered more relevant by various Indian Ocean Rim governments due to the direct impact on the coastlines. The regional programs are also really valuable for the reanalysis community. And INDUCE has prioritised that these dense daily to monthly observations of velocity, temperature and salinity across the ITF, the Agulhas and the Lewin Current are needed, and they're needed to be combined with hydrographic endpoints, similar to those used to measure the Atlantic overturning. So continuation of the existing Argo, satellite and Go Ship programs are really essential along with the regional efforts. But it's really quite a challenging environment to monitor because of their dynamics and the small time and length scales. So we really need innovative strategies for these integrated observing systems, such as combining the current meter arrays with gliders, with CPIs, and with hydrographic sections. And in this way, we'll get the important climate variables such as carbon, nutrient, and oxygen. And in addition to this, we need the innovation to be in real-time data return. So for the subsurface arrays, we need the fast telemetry and data pods. And coming to the last couple of slides now, the future strategies for INDUCE, particularly regarding connection to end users and stakeholders, really need to be better linked to regional and national efforts. And there are programs such as the Goose Regional Alliances which can help support this. And a key factor affecting investment in scientific research is really the level of national appreciation of the importance of the marine sector to the country's economy and resources. And the Goose GRAs are really in a unique position to be able to make the case to national governments and stakeholders through the IOC and ESCO. So in addition to support regional capacity development and involvement in sustained observations, these international partners need to be fostered and maintained, in particular within the Indian Ocean Rim countries. So as we've heard, bodies such as WMO and IOC, as well as other scientific bodies such as CLIVAR and SCORE, can really help facilitate this. And it's really essential to make sure that we improve evaluation mechanisms for what has been achieved to date and to consider the long-term thinking around funding mechanisms. So with constantly emerging new technologies and improving capabilities, there's little doubt that the global observing system is going to look very different in 10 years from now. And any future vision really needs to be flexible. Sensor developments will lead to a much greater range of variables being measured autonomously. Voluntary observing ships with automated equipment will enhance the system. And all of this will provide data for assimilation for models for operational oceanography. But really that data dissemination for the operational applications should form a key part of any vision of the observing system, as should end user engagement, because without this systematic approach, the stakeholder communities won't really realise the payoff of the in-situ observation, of the investments in in-situ observing. So really, just to finish, the effective communication and collaboration between scientists from different parts of the world needs to be enhanced, as does the sharing of knowledge, of data, of technology, and of equipment. And the communication to ocean and coastal communities is also really essential to avoid vandalism and to create awareness. And increasing the literacy of these communities of the benefit of these systems on their daily life is essential. And although we've seen now that capacity development has really changed and it's no longer a tick box, but the meaningful engagement that contributes to the observing system while aiding developing countries to manage their resources. But there's still a slight disconnect between international legal and policy framework and the reality of global ocean science collaboration. And we need to work on that. And just finally, ocean observing is not just technology. It's about people, and it's about a community of cultures and capabilities. And we need to strengthen and broaden this leadership. And that includes creating a new diverse generation of informed ocean scientists where ocean boundaries really aren't considered. And I'm super excited with how the IIOE2 Early Career Researchers Network works in this regard. And I really commend them and look forward to seeing their work continue. Thank you.
Juliet, as always, thank you for a very well prepared and excellent presentation. We really appreciate it. You've really inspired us, as always, and motivated us. We do have time for one quick question before we move on to Dr. Satish Shenoy. I would like to open up the floor for Juliet, please. Check the chat box. Don't see any chat.
Maybe when we have the panel discussions, people.
Right. Very good. Well, let's move on. Thank you again, Juliet. I would like to introduce Dr. Satish Shenoy, presently acting as a Ministry of Earth Sciences Chair Professor of the Government of India. Previously, he was Director of the Indian National Center for Ocean Information Services, INCOIS, Director as an additional charge of the National Institute of Ocean Technology, NIOT, in Chennai, Project Director as an additional charge of the Integrated Coastal and Marine Area Management, and Scientist at National Institute of Oceanography in Goa. Dr. Shenoy received his PhD in Oceanography from Cochin University of Science and Technology in 1984. Dr. Shenoy has contributed immensely to the field of air-sea interface in climate modulation and monsoon breeding. He has played a lead role in the Arabian Sea Monsoon Experiment, ARMEX, which changed the traditional view from a passive role for the ocean in monsoonal process to an active role in the monsoonal air-sea coupling. Dr. Shenoy's main research interests are in physical oceanography, observational oceanography, ocean currents, the impact of oceans on monsoons, and satellite oceanography. He has published more than 90 scientific papers, including research articles in peer-reviewed journals and conference proceedings. Dr. Shenoy has received several awards and honors, including the National Award in Ocean Science and Technology of India's Ministry of Earth Sciences in 2018, and received honorary doctorate degree, honoris causa, from AMET University in 2016. He is also a fellow of the India National Academy of Sciences, the Indian Academy of Sciences, Lagana State Academy of Sciences, Andhra Pradesh Academy of Sciences, and the Indian Geophysical Union. It gives me great pleasure to be with you today, Satish, and I would like to pass the floor to you, please, for your presentation.
Thank you, Sid. Can you hear me? I have a difficulty in unmuting.
Very clearly. We hear you very clearly, and we see your presentation. Please proceed.
The mic sign is not changing. Okay. So thank you, Sid, for the introduction, and let me thank the organizers for giving me this opportunity to present some of the ideas in this Indian Ocean Symposium. So the topic of my presentation is ocean services in India and their impacts on the end users. So the question arises is why do we need ocean information and services? That is the important question which comes on mind when you talk about ocean information and services. The ocean data and the information is the lifeblood for enabling marine policy, governance, sustainable development, and support the blue economic growth and scientific innovation. So it's a major driver of all these policies as well as for the economic growth. And the ocean services are essential for planning and carrying out the maritime activities and for ensuring safety of life and material at sea. So the Dr. Rajivan's talk clearly showed that how important the ocean is for the monsoons, which controls the economy of Southeast Asian region as such, plus the other regions in the world. So ocean plays a large role on the economy, the day-to-day life, and other activities of human beings. So to generate this information and services, the basic requirement is the generation of ocean data and information. You need data and information to generate more information from that, as well as generate the forecast or whatever it is. So though it is not the wonderful network of observations, earlier Sid also showed the Indus network, which mostly I have covered in this figure also. Though it is not the optimum network what we would like to have in the Indian Ocean, or the best network that we would like to have for the Indian Ocean, I will definitely say that it is a decent network right now we have, because I came through those years when there were no such observations or data available from the open ocean. So if we look at a similar picture 20 years back, we will see totally the blue ocean. There won't be anything in that. That was the situation. So we have made a tremendous progress over the past 10 or 15 or 20 years, not more than 20 years, I must say, in making observations using different type of platforms like Argo floats, drifters, mood arrays, XBT, then current meters, tide gauges, and of late the tsunami buoys. And the most important among them and the latest is the gliders, the autonomous gliders. And of course, the research ships collecting the data always remains on the top. Plus, the satellites provide a lot of data. And this data itself provides a lot of information. And I'm glad that IIOSC archives all this data from different platforms, the in situ platforms, as well as the remote sensing platforms, and also the model data, and makes it available for through different means like web, LAS server, or AirDAP, or even through offline through the CDs or or the pen drive or other means for students and academia, researchers, R&D institutions, and commercial users. So this itself is a great service which is being provided by IIOSC as a one-stop shop for the data. And this data is also quality checked following certain standards, but of course for the research it is the responsibility of the researchers to ensure the quality. And of late IIOSC also has developed the Digital Ocean for Data Services. Digital Ocean is a new platform which allows the integration of data from various type of platforms and generate the figures, as well as view the data in animations or whichever way you would like to but it pulls the data from almost every platform. For example, you would like to make a subset of not only for the region or the time, even a subset for temperature data. So whichever platform or whichever sensor provides data on temperature, all that will be pulled up, and the interpolations are done, or whatever is whatever you ask the platform to do, it does, and even displays how the data will looks like. This is a great service, I must say. Similarly, the water pollution is an important aspect for ocean management and the health of the population which is living on the coast as well as elsewhere. So in India, this monitoring of seawater quality has started sometime in 1990s. Some of those locations which are shown on the left-hand side a map of India are covered once in a season, at least 3 times a year, and some of them are monitored every month. So that generated a long-term data set, and now the NCCR in Chennai, another MOES institute in Chennai, has come up with the coastal water quality index, because if we had to tell the policymakers or the general public, it should be very condensed information. Otherwise, they will not be able to make out head or tail if you say that suspended sediment is so much or transparency is so much. So based on all that, using certain algorithms, they have come out with the water quality index. And now the efforts are made by NCCR as well as the IIOSC by developing autonomous sensors all along the coast, and the models are being developed so that the water quality can be predicted in short as well as in the medium range all along the Indian coast. In fact, right now such predictions are available for the Chennai coast, because that is where NCCR started working, and IIOSC is now expanding that work to other locations also. So this is another service which is being provided, which is very important from the point of view of UN Decade of the Ocean, the healthy ocean. And to ensure the health, you have to clearly monitor the quality of the waters, and also warn the people how that water can get deteriorated or can get better, so that the corrective measures can be taken. Another important service provided to the society is the potential fishing zone advisories, and this service is based on the data which is being received from the satellites sea surface temperature and the chlorophyll or water color from the satellite, and that data is used on a regular basis to identify certain features in the ocean waters like meanders, eddies, filaments, curvatures in the currents, etc., etc. And the potential fishing zone advisories have been marked on the map as well as provided as a text in a text format referring to certain known locations on the coast, so that the fishermen can refer to either to the map and use a GPS to navigate to that location and conduct fishing, or they can also look at the text and navigate to that location which is mentioned in the text and do that. And these services are being provided in different language. I think about 7 to 8 languages, because as many of us, you must be knowing that in India we have different languages. Each province, or what we call a state, they speak in different languages, and the large populations in each of the states can only speak in or understand that language. So these potential fishing zone advisories also are being provided in different languages for each of the states, so that they become very useful for the fishermen. So if we have stuck to the national language Hindi or English, the users wouldn't have used that much, and the actual real benefit wouldn't have come out from such services. Then the IIOSC has developed a suite of models, mathematical and numerical models, and the available data. The data is being utilized in these models, and various ocean state forecast products have been generated. And these products falls in 4 major categories: the daily forecast or the routine forecasts like wind speed, direction, wave period, height, direction, currents, ocean currents, speed and direction, the sea surface temperature, mixed layer depth, etc., etc. And also the warnings. These are not daily services, only based on the necessity. For example, tsunami early warnings, high wind wave alerts, because certain parts of the coast all of a sudden experiences high wind waves or swells. If they are by swells, they are in locally they are known as Kallakadal or rock seas, and they cause damages to the coast and the fishermen villages or the fishing gear which has been stored on the coast, etc. Similarly, this Perigean spring tide, which causes coastal flooding all of a sudden in that area, and the storm surges following the landfall of a cyclone. Similarly, the customized services are provided to the users depending on their requirements, like forecast along shipping routes, location-specific forecasts at different locations, and forecast for neighboring countries are being provided. I think 6 countries receive this forecast for their waters, and Navy and Coast Guard requires the forecast in certain formats and a certain way they should be. Similarly, the forecast for ports and harbors, forecast for maritime boats, island specific forecasts for Andaman Nicobar group of islands as well as Lakshadweep group of islands, and the for help for the emergency services like online oil spill advisory and search and rescue aid for searching if something is lost at sea. This is an example of the Kallakadal where the weather on the Indian coast is fine. There are no problems, but because of the storm in the southern ocean, the long period swells arrive at the Indian coast, and they are very powerful, and they create problems like. So these kind of information or the forecasts are given 3 to 5 days in advance, and normally those local newspapers pick that information, and then they also warn the local population about the possibility of such Kallakadal or the rock seas. And the second cutting shows they report that it happened as IIOSC had forecasted. Similarly, during the cyclone, IIOSC provides wave height forecasts at different all along the Indian coast, and also issues the joint bulletins together with the India Meteorological Department. And also IIOSC puts out this forecast and the observations wherever the observations are available from the wave rider buoys. For the one figure is here for the AD07, the mode data buoy of NIOT, how that buoy recorded the waves during the passage of the cyclone, and what was the forecast from IIOSC. Similarly, another wave rider buoy which is installed at Karwar, that how it recorded the wave heights and what is the forecast from the IIOSC and for Mumbai, Warsaw. So this helps in building the confidence in the users that the IIOSC forecasts are believable, because the IIOSC also puts out this comparison with observations and forecasts. So the search and marine rescue aid, which uses the forecasted surface currents and the winds from NCMR-WF or ECM-WF, and then generates the forecast or the probability location if a man overboard or a fishing boat which has gone missing, and provides this information to the Indian Coast Guard, which is the agency which has to do these search operations at sea. So they depend on this kind of information to conduct their search and to restrict the search location to certain areas so that they need not search for the entire region, and that helps them in many ways. Similarly, the oil spill, whenever the oil spill occurs, the Coast Guard informs the inquirers that so much oil has been spilled at so and so location, and please tell us how this oil will move to which direction, which locations, and what would be the percentage of oil that will be carrying as it moves away from the spill location. So these kind of services are being provided to Indian Coast Guard, and soon after the occurrence of Indian Ocean tsunami in 2014, Ministry of Earth Sciences was tasked by Government of India to establish a Indian early tsunami warning system, and Ministry tasked the inquiries to do that job, and the fully operational system is functioning since 2017, which is self-contained, which has the observational networks or data reception capabilities from the seismic network from all over the world, not only the Indian seismic network, even from the other countries' seismic networks, and bottom pressure recorder network, and also the sea level gauge or tide gauge network. All these networks report the data, or inquirers receives the data at the center through various means, either through satellite communications or GPRS communication, and use that information to generate the warnings together with a numerical model, and provides the tsunami warnings to the end user. And the sender has achieved the capabilities not only to give generalized early warning, rather it provides location specific warning at the coast, which part of the coast is going to get affected by the tsunami wave, and what is the expected wave height at that location. And also recently the 3D GIS maps of certain parts of the coast have been generated, and right now the center has the capability to provide what is the level of inundation on the coast, and how far this inundation will penetrate on the coast. And also it can provide that 3D GIS map with the buildings and all the details of infrastructure on the coast to the disaster management agencies. So we have come a long way in tsunami early warning services. Similarly, the storm surge warning services also, as following the predictions received from the IMD on the path and intensity of the cyclone, and location of the groundfall, landfall inquiries generates these kind of maps showing the storm surge inundations. And the integrated flood warning system for Chennai and Mumbai, both are metropolitan cities on the coast, and NCCR Chennai has made this operational for both these cities, and I think they are working for other coastal cities as well, so that the flooding can be forewarned. And how inquires disseminates this information to the end users, because even if we generate this kind of information, whether the advisories or forecasts or early warnings, they should reach the end user at right time, especially when there is a tsunami early warning or storm surge warning, etc., etc. All this has to be communicated. For that, the many communication means have been adopted, and the most popular now is the mobile service. And one drawback of mobile service is, especially for disseminating the potential phishing zone advisories, is the fishermen, once they leave the coast and go out at the sea, they are no longer able to receive the mobile signal and they don't receive the information. And recently that problem has been solved by using the geostationary satellites or a group of satellites called Gagan, which is specifically designed to provide location accuracies for the airports. And the inquiries collaborated with the Airport Authority of India, and they had a unused message in their data stream that has been used, and a system called Gemini has been put to operation, so that fishermen will get this information on potential fishing zone advisories, as well as the ocean forecast or any warnings on tsunami or any of those kind of things, even if they are far out at sea, so that they can plan their arrival to the nearest coast and save themselves. And what are the benefits of this potential fishing zone advisories? For example, without potential fishing zone advisories, mostly the fishermen spend a lot of time in search of the fish school to cast their net. So more fuel has been consumed, so that adds to the increased carbon dioxide emission. And the effort is huge, because sometimes they have to search for hours and hours or days and days. And sometimes they will not be able to locate the right fishing ground to conduct the fish catch. So the catch is poor and they get very little profits from that. Whereas when they started using the advisories, their search time has completely disappeared or reduced drastically, and that itself helped them in saving the diesel. They spend less on the diesel, and they can directly go to that fish stall, and they rightly hit at the right fish shoal, so that they can get a better catch, and their profits also has been increased by 2 to 4 times. And various agencies have conducted some of these studies on how it helps in reducing the environmental problems, like National Agricultural Innovation Project. They conducted a study involving 32 fishing boats in Raigad district of Maharashtra, and they found that they are able to save a lot of diesel, which amounts to 1,15,000 kilograms of carbon dioxide emission. Similarly, a lot of validation experiments have been conducted. I think, if I remember correct, more than 600 validation experiments have been conducted, and they also gives the similar numbers of benefit. And Central Marine Fisheries Research Institute conducted another study, and they found that the greenhouse gas emission gets reduced if fishermen use this kind of information for their fishing. Similarly,
Satish,
the economic
could you wrap it up in 1 minute? Thank you, sir.
This is the
Thank you.
last slide. The economic benefits also are tremendous. This has come out from the professional agencies, studies like National Council of Applied Economic Research. They brought out 3 reports, 2010, 15, and 2020, And I don't want to read through this this slide, but you can see that kind of numbers which has been put there. It gives a lot of benefit, not only from potential phishing zone advisories, even from the ocean state forecast, as well as the tsunami early warnings, etc., etc. So the ocean services and information are essential for the economic growth and environmental benefit, as well as for the wellness of the society. Thank you very much.
Thank you very much, Satish, for clearly outlining the practical applications as well as the economic benefits. I think that's a big part of this as we try to implement all this with the agencies. So thank you, Satish. Thank you very much for excellent presentation. I would like to move into the panel discussion at this point. So I'd like to invite Anish to please bring up my earlier presentation so we could quickly review the 4 questions I've asked the panelists to address. And we'll take about 5 minutes for each of these questions before we conclude this observations to services plenary panel discussion. Anish, could you bring up that one slide, please, that has the panel questions? Thank you. Next, please. One more, please. So these are the 4 questions. What are the new developments towards sustainable ocean observing system? How new age autonomous instrumentation such as gliders, which we've heard a lot about today, drones, etc., can be used for sustained ocean observations? What could be probable strategies to enhance the multi-hazard early warning services, including predictions for the ocean, climate, and weather? And what will be our most important contribution to the UN decade? And I will report this out tomorrow during the plenary discussion with Dr. Vladimir Ryabinin, who will be discussing the UN decade. So with that, I'd like to open it up. Let's take about 5 minutes and let's drill down and unpack, what are the new developments towards sustainable ocean observing system? What technology innovation that will help us take observations to services? The floor is open, please. If you could please turn on your cameras if you're a panelist. Juliet, thank you. Thank you. And if Secretary Rajivan is still with us, if he could turn on his camera. So some of you mentioned these in your presentations, but I'd like to unpack these, please, and not only what is emerging, but
right now the issue with the glider, one of the bottleneck with the glider is you have to go back and pick it for servicing and redeployment, which itself is a huge cost because organizing a ship and other logistics and going back to do that. So I feel that another 5 years time these gliders
would like to move on to our fourth and final question. And this is the one I will be reporting out tomorrow during the plenary discussion for the UN decade led by Dr. Vladimir Ryabinin. What will be our most important contribution to the UN decade? So for this panel, the ocean or observations to services, what will be our most important contribution to the UN decade within that realm, within that context? Please, the floor is open.
So, if I may, Sid, one thing
Please,
that I thought about really was that with the focus on sort of the Indian Ocean community, the Indian Ocean community could really be an exemplar for the Ocean Decade of sharing, unbiased sharing of data, knowledge, capacity, technology, and infrastructure amongst Indian Ocean rim countries. So I think we could really set ourselves up to be an exemplar over the next 10 years in doing this.
Music to my heart. That's just what I'm thinking too, Julia. Thank you very much. We know the players. We're a tight community. We know each other. We have a great infrastructure. We have a great data management system. And now let's just pull it together for specific exemplars. I couldn't agree more. Any comments, please, from Dr. Dahamalad or Dr. Shenoy? Okay.
Yeah, I think Juliet has nicely summarized what we can contribute to the decade of the ocean. So that data sharing the knowledge and our efforts to keep the healthy ocean, like monitoring the pollutants and the water quality, etc., and also the safe ocean. So these are the contributions from our community in the Indian Ocean we can make to the decade of the UN decade of the ocean science.
Thank you, Satish. That's a very nice way to summarize it, consistent with their objectives of the UN decade. That's very helpful. Okay, any other concluding remarks? We are at the top of the hour, and I would like to thank all of our participants, Secretary Rajivan, Dr. Dilmaha Mad, Dr. Juliet Hermes, and Dr. Satish Shenoy. Thank you very much for your excellent presentations and for your insightful comments for this panel. This will conclude this panel discussion. I would like to thank Anish and Sushant for your extremely helpful support in bringing this panel to a successful conclusion. This is the end of the panel. Have a great day, great night, and thank you very much.
Thank you, Sid.
Thank you.
Thank you, Sid, for being there for late night or early morning, and all the panelists for their very valuable time and contribution. So for all other audience, don't miss the concluding panel discussion on 18th. That will be at 14:30 IST and 900 UTC. So there we'll be discussing on the contribution to United Nations Decade of Ocean Sciences for Sustainable Development. So thank you.
Thank you very much,
Thank you.
Anish.
Bye.
Thank you. Bye, Satish.
Bye.